All right, so this standard is 90% heating curves. There are a couple little times they could throw in some other graphs, but if you want, you can watch the potential energy graphs standard, or you can watch the phase diagram one again. But primarily what you should be seeing on this part is just the heating curves. So what is a heating curve? This is what one looks like. Make sure you're reading everyone carefully. They all look a little bit different. All right, so first off, temperature here, that's the y-axis, and it is almost always degrees Celsius because we're in thermodynamics. Down here, amount of heat added. Sometimes they do have some values associated with 1 mole of the substance. Typically, you'd see it in a kilojoules variety, but not always. You just have to know that this heat down here is we have 0 heat added. And then over here, we have a lot of heat added because we're going to the right and increasing our heat. Now, some of you are going, but wait, aren't heat and temperature the same thing? Heat is our thermal energy, okay, with joules or kilojoules. Temperature is a measure of the kinetic energy. Okay, so when you read a thermometer, you're reading how much kinetic energy something has. So if we have a low temperature, we have a low kinetic energy. We have a high temperature, we have a high kinetic energy. Does this make sense? Yeah, because when we are freezing cold, we're going to have a low energy level. We're going to have a low kinetic energy, and same with chemicals. I always go back to ice because it's easy. So when we are in solid form, those molecules are just vibrating in place, super low kinetic energy. Okay? And then we change to that liquid phase. We have a little bit more kinetic energy. And then finally, we get up to that gas phase where we have the random particles moving all over the place, different speeds, different directions, all sorts of crazy, high kinetic energy. What else is different about this guy? This guy has low IMF. He doesn't have a lot of cohesion holding together, where a solid of the same substance would have high IMF if you are comparing the two. Okay? So that's our relationship here. So with that, we can make some inferences. This first line down here, we're heating something. How do we know we're heating it? The amount of heat was changed, a teeny tiny amount of heat, but there was an amount of heat added, and our temperature went up 10 degrees. So in this thing, something is being heated. What state of matter? We're at our coldest. It's a solid. So even though when you're looking at a mug and you're like, well, that's not at its coldest, it is because it's in solid form. Think about ice to keep it in track. So this first line here is our solid line. So if you are talked about any temperature between -10 and 0, that would be in solid form. So you could look on the graph for the temperature to see what happens. Then what happens when we get to this first little line here? That's when the solid begins to melt. So even if they hadn't said H2O in solid form here, you might have been able to guess because you see the 0 degrees here. Now, some other substances can have a 0 degrees melting point, but we know for sure water does. And so this just confirms it. The water's in its solid form, and then it begins to melt at 0 degrees. So while it's melting, it's both a solid and a liquid because that depends on how much substance it is. If I have that ice cube again, and I take it out and put it on the counter, it just doesn't magically turn instantly into the puddle of liquid. It takes time, it drips, it goes through a process. So while it's there, it's slowly being converted from a solid to a liquid. So there's some solid and some liquid through this whole process. And then at the end of the process, all the solid is melted. What's weird about this guy? This guy's 0 slope. There is no increased temperature. But look at this. There is heat added. That heat had to go somewhere. It was taken inside. Oh, inside. Something is taken inside, it's endothermic. We had to add heat to get something to go from a solid to a liquid. Oh, that makes sense. I know we have to add heat to go from a solid to liquid if I'm thinking about an ice cube. So that makes sense. This is an endothermic process. So as we're adding heat, we are going through endothermic processes. So what does that make this next red line? If we were at a solid and we melted, we're now at a liquid. And then we have a horizontal line again, no change in temperature. So that is where another phase change is happening. The phase change again is endothermic. We're taking the energy inside, so we're not increasing the kinetic energy of the particle. We're not increasing the temperature, zero slope. So the liquid begins to boil, or the liquid begins to evaporate, or the liquid begins to vaporize. For year one, those are not exact synonyms, but you can think about it that way. And so we have gas and liquid water at the same time right here until there's no more liquid. And finally, we end up with a gas. Now that horizontal line was at 100 degrees. So if you just went to the left on that same path, you're going to be able to read the boiling point off the graph. So when you see those horizontal lines, the bottom horizontal line is always the melting point, regardless of where it is on the temperature scale. And the top horizontal line is going to be your boiling point. So that's how you can keep track of which thing is where. What if we're reading the map or the graph this way? Then we'd be losing heat. When we're losing heat, what happened to the heat? It exited, exothermic. So if we're going from a gas to a liquid, and we're going the reverse way, we are going to be losing kinetic energy, losing temperature, and so it is an exothermic process. We had to release that energy so that we could go down. That's how we made it colder. Now we have some equations to go with it, okay? The blue are phase change lines, so the Q is equal to, or the heat is equal to either N delta H or M delta H. That's if you are calculating something anywhere on any of the blue lines, large or small, but only on the blue. Now, why are there two equations? This is where unit analysis comes into play. On the table they could give you delta H in kilojoules per mole. They could give you delta H in kilojoules per gram. Technically, they could give it to you in grams per joule or joules per gram too. But the main thing to remember is this is unit analysis. If I have kilojoules per mole and I want to get kilojoules, what's the only thing I can multiply by? By moles. So if your kilojoules, or if your delta H, your change in enthalpy is kilojoules per mole, then you are going to multiply by the moles to get your answer. If your units are kilojoules per gram, you're going to multiply by the grams, but it's still going to give you your Q, your heat at the end. So you can still calculate your Q, just be aware of your units. What if we want to calculate the Q on the diagonal lines? That's what we've already been doing, your MCAT equation. In this case, the Q is going to be in joules, where in the flat areas, it's usually in kilojoules. So if you have to add them together, make sure your units match. Okay. How would we know this? Oftentimes, they're going to give you the C value, which is the specific heat. The specific heat is going to have something like joules per gram degrees Celsius. You could still use your unit analysis that way. So my energy has to be in joules for this guy. My mass is going to have to be grams. And my degrees C is going to be temperature. So even if you didn't know the MCAT equation, you could kind of break it down. Joules per gram degrees C. Okay, I got to multiply by the grams and the degrees C to be left with just joules. That's where it came from. I multiplied by the grams and the degrees C. So there's a lot of information that's hidden in those items. Do you need to know all that? No. You need to know the flat areas. You're going to N delta H or M delta H to find your heat, to find your Q value. The red lines, you're going to use the MCAT equation. All right, so exo or endo. So we did really talk about this already. Look at the graph. If the graph is going to the right and we're adding heat, we had to take it inside. So that is endo. But if they want us to go, and that's when we're increasing the temperature to, so that would be your endo areas. So if we're going down in temperature or losing heat, then it is exo. So you can go through each problem when it tells you the points on the graph, plot them on there and see which direction we're going. And there are your little logic checks to make sure, oh, that makes sense that it would be positive or negative. Endothermic is positive, we're taking it inside. Exothermic is negative. We want that energy, but it's leaving us, so it's making us sad. Okay. What is the lowest temperature that this guy is a liquid? So where is our liquid line? This red line here, the bottom of the red line is at 0 degrees. That's at its melting point. That makes sense because it's melting through there. So it's changing, or sorry, in this direction, it would be what? Freezing point. Because it is in the process of freezing to a solid. So last time it's going to be a liquid is at 0 degrees. Which phase has the lowest kinetic energy? Kinetic energy is related to temperature. So your lowest kinetic energy is when it is a solid, vibrating in place. Determine the total kilojoules of 5 grams of water between 5 and 60. So kilojoules is a Q, so I'm going to need one of the Q equations. 5 grams, that's a mass. Water, H2O, so I can use that curve, between 5 and 60 degrees. So you're looking at it and going, but wait, we've done this equation already, and we didn't need the heating curve. No, your heating curve in this case is just a double check, especially if they don't give you numbers. But even if they do give you numbers, this is not 1 mole of water. So you still would have to break down and use the stuff. So let's just map on here. Where is 5 and 60 degrees? 5 and 60 degrees. This is all in one line. The line is a diagonal line. The line has a change in temperature. If you have a change in temperature, there's only one equation you can use, the MCAT equation. You can't use the MCAT equation on the blue line because there's no change in temperature. So Q equals MC delta T. We want to find Q, so that's our unknown. We have a mass. We don't have a specific heat. If they do not give it to you in a problem, use the standard specific heat. It doesn't actually work in every single part, but 4.184 joules per gram degree C, that's the specific heat of water. And that's also the conversion that you've used to go between joules and calories. So that's why they kind of expect you to memorize it. If you're on the test and they do not give it to you on this problem, page back or page forward, flag this question and find where it's written, because usually it's written in some other random area. Same with your polyatomics. It'll say H2SO4. What is the name of that? And you'll be like, oh, I don't remember. Page forward and page back. And usually somewhere along the way, it told you that that is sulfuric acid. With the new SOLs, I don't know if that's still going to happen, but that's what used to happen. Okay, so we have an M, we have a C, a delta T. What is delta T? The change in temperature. Delta is just the Greek letter. The change from temperature final minus temperature initial. Temperature final, or the ending temperature, 60 minus 5 is 55. Go slowly on your direction or you might end up with the wrong sign with the Q. But if you get the wrong sign with the Q and it doesn't logically make sense, you can always change it later. Yep. So we have an MC and a delta T. So now we can solve. Okay. 5 times 4.184 times the quantity of 60 minus 5, and that gives us 1,150.6 joules. Okay, remember in these equations, our Q is in joules because our specific heat was in joules. But we are not done here. Why not? We didn't worry about sig figs. Make sure you don't forget 1 sig fig, 4 sig figs, and this guy we're doing subtraction, so it's going to be 0 decimal places. So 55 degrees has 0 decimal places, so that's 2 sig figs. That's the higher level one, and it does not matter. We have 1 sig fig, so our answer has to be rounded to the first sig fig. Here's my first sig fig. It's in the thousandths place, so we're either rounding down to 1,000 or we're rounding up to 2,000. We're going to round down to 1,000 here. If when you look at the results are in kilojoules, make sure you convert. To go from joules to kilojoules, it's dividing by 1,000. On the SOL, no conversions. Make sure you have them memorized. Go watch some of the other videos to get some idea on how to do those conversions. All right, this time we're determining the kilojoules of 1 mole of water at 1.0 times 10 to the second degrees C. All right, this is a positive exponent because if they don't list it, it's positive. And the 2 means 2 hops. We're going to be making the number bigger because it's a positive exponent, so it makes the guy bigger. 2 hops to the right, we're going to make bigger, 100 degrees C. So we're going to be here. What is this point called again? It has the flat line. It has the top flat line. This is the boiling point. Okay, so this water right now is boiling. It does not have an increase in temperature. I can't use the MCAT equation. I cannot use the MCAT equation here because it's entirely on that flat area. So what do I have to use? N delta H. There's 4 delta H's down here. Do I want the heat of fusion, the heat of solidification, the heat of vaporization, the heat of condensation? Hey, wait a second. Those guys look the same except for the negative. Wait a second. Maybe this isn't as complicated as I thought. Where is fusion and solidification? Down here. How do I know that? Because fusion is going from a solid to a liquid, and solidification is going from a liquid to solid. So the only place I could use those delta H's would be on that line. So what about up here? Oh, vaporization, liquid to gas, condensation, gas to a liquid. So I'm going to be using 40.8. I just now got to figure out if my delta H is positive 40.8 or if my delta H is negative 40.8. Is there any other clues? Endothermic process. Endo, taking heat inside. So endothermic is when we're going to the right. So when we're going from a liquid to a gas. Which one of those is liquid to gas? This guy right here. So I'm going to use my delta H value as 40.8 kilojoules per mole. Look at that. I don't even have to memorize what the heat equation is. I just need to know that if I multiply by moles, I'm going to get the kilojoules. Multiply by 1 mole. I just had to make sure I had the right delta H. And so there is my answer when we are going through that way. 2 sig figs. So 2 sig figs in my answer. So there is a little bit of overview about all the different things that can come up with heating curves.